Beneath your feet, as you walk through any forest, lies a communication network more sophisticated than anything humans have ever built. The forest floor appears static, carpeted with fallen leaves and scattered debris, but this peaceful surface conceals one of nature's most remarkable achievements. Here, in the rich darkness of soil and decomposing matter, an ancient internet pulses with constant activity, connecting every tree, shrub, and plant in an intricate web of mutual support and shared intelligence. The morning light filters through the canopy above, casting shifting patterns across the woodland floor, while beneath this tranquil scene, millions of thread-like structures weave through the earth in a network so vast and complex that a single handful of forest soil contains more connections than there are stars in the known universe. These are not the rigid cables and fiber-optic networks of human technology, but living conduits that have been perfecting their communication protocols for over 400 million years. In this hidden realm, messages travel not as electrical impulses or digital packets, but as chemical signals that carry information about weather patterns, insect attacks, drought conditions, and seasonal changes. The network operates continuously, processing and routing information with an efficiency that would make any telecommunications engineer marvel at its design. Unlike human networks that require constant maintenance and frequent updates, this biological internet has been running without interruption since before the first dinosaurs walked the earth. The architects of this underground communication system are neither plant nor animal, but something far more ancient and mysterious. Fungi, those remarkable organisms that exist in the liminal space between kingdoms, have evolved to become nature's ultimate networkers. Their microscopic threads, finer than spider silk and more extensive than the most ambitious subway system, penetrate every cubic inch of healthy forest soil, creating a living matrix that connects the forest in ways that challenge our understanding of what it means to be an individual organism. What makes this network truly extraordinary is not just its scope, but its intelligence. The system can prioritize urgent messages, reroute communications around damaged areas, and even make complex decisions about resource allocation that benefit the entire forest community. When a tree comes under attack from insects, chemical distress signals race through the underground network faster than the pests can spread, alerting neighboring trees to begin producing defensive compounds. When drought threatens one area, water and nutrients flow through the network from regions of abundance to those in need, maintaining the health of the whole forest ecosystem. This is not merely a passive transport system, but an active, decision-making network that exhibits behaviors remarkably similar to artificial intelligence. The fungi and their plant partners engage in complex negotiations, trading resources based on current needs and future projections. They maintain detailed chemical records of past interactions, building trust and establishing long-term partnerships that can span centuries. The network learns from experience, adapting its protocols to changing conditions and optimizing its performance over time. The forest floor reveals few hints of the extraordinary complexity hidden beneath its surface. Occasional mushrooms push through the leaf litter like periscopes from a submarine, offering brief glimpses of the vast mycelial networks spreading through the darkness below. These visible fruiting bodies represent only a tiny fraction of the fungal organism, much like icebergs revealing only their peaks above the ocean surface. The true body of these fungi exists as an invisible web of hair-thin threads called hyphae, creating what mycologists call the mycelium, a living internet that connects the forest in ways both profound and beautiful. Every step you take crosses thousands of these biological data cables, each one humming with chemical conversations between distant trees. A towering oak might be sharing carbon with a struggling maple seedling 50 feet away, while simultaneously receiving phosphorus from a cluster of birch trees and sending alarm signals about an aphid infestation to the entire network. This constant exchange of resources and information creates a forest that functions less like a collection of individual trees competing for survival, and more like a single vast organism with a distributed nervous system. The implications of this discovery transform our understanding of forests from collections of individual trees into integrated communities with their own forms of collective intelligence. Each tree exists not as an isolated organism, but as a node in a vast network that shares resources, information, and even maternal care through underground connections that blur the boundaries between self and other, individual and community, competition and cooperation in ways that challenge our most fundamental assumptions about how life organizes itself on this planet. The conditions that gave birth to this underground internet were forged in the crucible of survival itself. 400 million years ago, when the first primitive plants ventured from the safety of aquatic environments onto the harsh, mineral-poor landscape of early Earth, they faced challenges that would have overwhelmed any individual organism. The terrestrial world offered abundant sunlight for photosynthesis, but the rocky soils held their nutrients in forms that plant roots could never hope to access alone. It was in this moment of desperate need that one of evolution's most elegant partnerships was born. The ancient soils were locked vaults of essential minerals, their treasures bound in crystalline structures that resisted all attempts at extraction. Phosphorus, nitrogen, potassium, and countless trace elements lay tantalizingly close to the struggling plant roots, yet remained as inaccessible as if they were buried beneath miles of solid rock. The early plants possessed the biological machinery to harness the sun's energy through photosynthesis, creating the sugars and carbohydrates that would become the foundation of all terrestrial life, but they lacked the chemical keys needed to unlock the mineral wealth hidden in the soil around them. Into this environmental impasse stepped the fungi, organisms that had already spent millions of years perfecting the art of chemical decomposition. Unlike plants, fungi were master chemists, capable of producing powerful enzymes that could dissolve the most stubborn mineral bonds and release nutrients from seemingly sterile rock. Their hyphal threads could penetrate the microscopic cracks and crevices in soil particles, reaching spaces far too small for even the finest plant roots to enter. Where plants saw impenetrable barriers, fungi saw opportunities for chemical mining on a scale that would make human extraction industries seem primitive by comparison. The partnership that emerged from this mutual need created the first version of the underground internet, a revolutionary communication and resource-sharing network that would transform the terrestrial world. Plants would channel their excess photosynthetic products, rich carbohydrates and sugars, down through their roots to feed their fungal partners. In return, the fungi would use their chemical expertise to extract minerals from the soil and deliver them directly to the plant roots through an intricate network of hyphal connections. This elegant trade agreement, sealed not with contracts, but with chemical handshakes, created the foundation for every forest ecosystem that would ever exist. The environmental pressures that shaped this partnership continue to drive its evolution today. Modern forests face a complex array of challenges that would overwhelm any individual tree attempting to survive alone. Seasonal variations in rainfall create periods of drought that can last for months, while unexpected flooding can waterlog soils and starve roots of oxygen. Insect outbreaks can strip the leaves from thousands of trees in a matter of days, while fungal pathogens spread invisible diseases that can kill entire groves. Temperature fluctuations stress plant metabolism, while soil chemistry shifts with changing weather patterns and human activities. Each of these environmental pressures has contributed to the sophistication of the underground network. Drought conditions favor trees that can access water through the extensive hyphal networks, which can extend far beyond the reach of individual root systems. During dry periods, the fungal partners act as long-distance water carriers. The network creates a kind of hydraulic internet, distributing water resources based on need rather than proximity, ensuring that even trees in the driest locations can access the moisture they need to survive. The threat of insect attacks has driven the evolution of the network's communication capabilities. When bark beetles bore into a tree's trunk, or caterpillars begin devouring its leaves, chemical alarm signals flood through the underground network faster than the pests themselves can spread. These molecular messages carry detailed information about the specific type of threat, allowing receiving trees to produce precisely targeted defensive compounds before the attackers arrive. The network functions as an early warning system that would be the envy of any military strategist, providing real-time intelligence about threats moving through the forest canopy. Nutrient scarcity in forest soils has created another layer of network sophistication. Different tree species have varying nutritional needs throughout their life cycles, and the underground internet has evolved to accommodate these changing demands. Young seedlings, struggling to establish themselves in the deep shade of the forest floor, receive nutritional support from mature trees through the network, even when those mature trees belong to different species. Elderly trees, approaching the end of their lives, often channel their remaining resources back into the network, creating a kind of inheritance system that enriches the soil for future generations. The seasonal rhythms that govern forest life have shaped the network's temporal intelligence. As autumn approaches and deciduous trees begin to withdraw nutrients from their leaves, the underground network shifts into a different operational mode. Resources that were flowing upward to support summer growth begin moving laterally through the soil, redistributed to evergreen species that will maintain photosynthetic activity throughout the winter months. The network maintains a kind of seasonal memory, adjusting its resource allocation patterns based on historical data encoded in the chemical signatures of previous years. Climate variability has pushed the network toward ever greater resilience and adaptability. The hyphal threads can rapidly extend into new areas when environmental conditions change, creating alternative pathways for communication and resource transport. When storms topple trees and break established network connections, the fungi quickly grow new bridges to restore communication links. The system exhibits a kind of biological redundancy that ensures network integrity, even when individual components fail, much like the Internet protocols that automatically reroute data around damaged servers. These environmental pressures have created an underground Internet that operates according to principles of mutual aid and collective resilience that challenge our understanding of competition in nature. Rather than each tree fighting individually for survival, the network enables a form of cooperation that makes the entire forest more robust and adaptable than any individual organism could ever be alone. The players in this underground internet are unlike the standardized components of human networks. Each participant brings unique capabilities, specialized adaptations, and distinct personalities shaped by millions of years of evolutionary refinement. The forest's communication system succeeds precisely because of this diversity, creating a network where different species contribute complementary strengths to build something far more sophisticated than any single organism could achieve alone. At the heart of the network stand the trees themselves, transformed from simple individual organisms into complex network nodes with specialized communication equipment. Each tree has evolved an intricate root system that functions less like traditional anchors and more like biological routers, equipped with thousands of connection points where fungal partners can interface directly with the tree's internal transport systems. These are not the simple spreading roots that most people imagine, but sophisticated underground architectures tailored to each species' networking strategy. The mighty Douglas fir, reaching heights that dwarf cathedral spires, develops what forest ecologists call a hub-root system that makes it one of the network's most influential nodes. These ancient giants send their roots, spreading in all directions for hundreds of feet, creating vast underground territories where they can establish connections with dozens of different fungal species simultaneously. Their root tips are equipped with specialized cells that can distinguish between beneficial partners and potential threats, allowing them to be highly selective about which organisms they allow into their network. A single mature Douglas fir may maintain active connections with over 20 different fungal species, each partnership optimized for different types of resource exchange and communication. The graceful birch trees, with their distinctive white bark and delicate leaves, have evolved an entirely different networking strategy. Rather than building massive hub systems, birches excel at rapid network deployment and flexible partnerships. Their fine hair-like roots can quickly establish new connections and just as quickly dissolve them when conditions change. Birches function as the network's rapid response team, able to quickly extend communication links into disturbed areas and help newly arrived seedlings connect to the established network. Their shallow root systems make them excellent interfaces between the deep network infrastructure and the surface layers of soil, where many smaller plants struggle to establish connections. The ancient oaks, those monarchs of the temperate forest, bring a different kind of networking expertise to the underground internet. Their massive taproot systems plunge deep into the earth, often reaching groundwater sources that lie far below the shallow root zones of other species. Oaks serve as the network's deep water specialists, acting as biological wells that can draw moisture from profound depths and share it with the entire community through their extensive fungal partnerships. Their root systems can persist for centuries, creating some of the network's most stable and long-lasting communication channels. The evergreen conifers, from towering pines to sprawling spruces, contribute year-round networking capabilities that keep the underground internet operational even during the dormant winter months, while deciduous trees withdraw their energy and reduce their network activity during autumn. The conifers maintain active photosynthesis and continue feeding their fungal partners throughout the coldest months. This seasonal constancy makes them essential network infrastructure, ensuring that communication pathways remain open and that the underground internet never completely shuts down. But the trees, impressive as they are, represent only half of the networking partnership. The true architects of the underground internet are the fungi, organisms so uniquely adapted for network construction that they seem to have been designed specifically for this purpose. These remarkable beings exist in a biological category entirely their own, neither plant nor animal, but something far more ancient and mysterious. They are the living cables, routers, and network protocols of the forest communication system. The mycorrhizal fungi, whose name literally means fungus root, have evolved into specialized network engineers with capabilities that surpass anything in human technology. Their bodies consist entirely of microscopic threads called hyphae, each one finer than spider silk yet stronger than steel cable of comparable thickness. A single fungal organism can extend these hyphal networks across acres of forest floor, creating a living infrastructure that connects hundreds of trees in an intricate web of mutual support and shared information. Different fungal species bring distinct networking specializations to the forest internet. The ectomycorrhizal fungi, which form partnerships primarily with trees like oaks, pines, and birches, create external networks that wrap around root tips like biological fiber optic cables. These fungi excel at long-distance communication and resource transport, capable of moving nutrients and water across distances that would challenge any individual tree root system. Their hyphal networks can extend for miles through the forest soil, creating superhighways for information and resource exchange. The arbuscular mycorrhizal fungi pursue a different networking strategy, actually penetrating into the root cells of their plant partners to create internal communication networks. These fungi specialize in intimate high-bandwidth connections that allow for extremely rapid exchange of both resources and information. While their networks may not extend as far as their ectomycorrhizal cousins, they create connections of extraordinary depth and complexity, facilitating communication that approaches the speed and sophistication of neural networks. The Wood Wide Web also includes specialist fungi that serve unique networking functions. Some species act as biological bridges, connecting different types of mycorrhizal networks that would otherwise remain isolated. Others function as network security specialists, producing compounds that protect the communication channels from pathogenic organisms that might try to infiltrate or disrupt the system. Still others serve as network maintenance crews, breaking down damaged hyphal connections and recycling their components to build new communication pathways. Perhaps most remarkably, some fungal species have evolved to become network coordinators, organisms that seem to actively manage the flow of information and resources through the underground internet. These coordinator fungi can sense the nutritional status of different trees across vast areas and direct resources toward those most in need. They appear to make complex decisions about network routing and resource allocation, exhibiting behaviors that suggest a form of distributed intelligence that emerges from the network itself. The underground internet succeeds because each participant brings irreplaceable capabilities to the network. Trees provide the photosynthetic energy that powers the entire system, while fungi contribute the chemical expertise and physical infrastructure needed for long-distance communication. Together, they have created a biological network that operates according to principles of cooperation and mutual benefit that challenge our understanding of how complex systems organize themselves in the natural world. This diverse community of network participants has transformed the forest from a collection of competing individuals into an integrated communication network where information flows freely and resources are shared according to need, rather than proximity. The underground internet represents one of evolution's most elegant solutions to the challenge of creating resilient, adaptive systems that can thrive in an uncertain and constantly changing world. The daily routines of network participants reveal behaviors so sophisticated they challenge our understanding of intelligence in non-human systems. Each morning, as the first rays of sunlight penetrate the forest canopy, the underground internet awakens with a surge of activity that rivals the morning rush hour of any major city. Trees begin their photosynthetic processes, converting sunlight into the sugars that fuel the entire network, while their fungal partners adjust their hyphal networks to optimize the day's resource distribution and communication protocols. The Douglas firs, those towering network hubs, begin each day with what can only be described through chemical signals sent down their roots. They query their fungal partners about network conditions, soil moisture levels, and any threats detected during the night. These ancient giants have evolved a remarkable ability to prioritize their partnerships based on current conditions. During dry periods, they strengthen connections with fungi that specialize in water extraction from deep soil layers. When insect threats are detected, they enhance partnerships with fungi that excel at rapid communication, ensuring that alarm signals can spread quickly through their section of the network. The behavioral strategies of mature Douglas firs reveal a kind of network management that borders on conscious decision-making. When a large fir detects that a neighboring tree is under stress, it can actively redirect resources through its fungal partners to provide assistance. This is not a passive response, but a deliberate reallocation that requires the tree to sacrifice some of its own resources for the benefit of the community. Even more remarkably, Douglas firs have been observed providing extra support to their own offspring, channeling additional nutrients through the network to young firs struggling to establish themselves in the competitive understory environment. The birch trees operate according to entirely different behavioral principles that make them the network's most adaptable participants. These graceful trees have evolved a strategy of rapid partnership formation and dissolution that allows them to respond quickly to changing conditions. A birch can establish a new fungal connection in a matter of hours and dissolve an unproductive partnership just as quickly. This flexibility makes birches excellent at exploring new areas of the forest and establishing network coverage in regions where other trees have not yet ventured. Birches also exhibit remarkable seasonal behavior patterns that optimize their network contributions throughout the year. During spring and early summer, when their rapid growth and high photosynthetic output generate surplus energy, birches become generous network contributors, sharing excess resources with slower-growing neighbors. As autumn approaches and they prepare for dormancy, birches systematically withdraw their resources from the network while simultaneously strengthening their connections with evergreen partners that will maintain network activity through the winter months. The ancient oaks demonstrate perhaps the most complex individual behaviors in the entire network. These long-lived giants develop what forest researchers call institutional memory, maintaining detailed chemical records of network interactions that can span decades. An oak tree can remember which fungal partners proved most reliable during previous droughts, which communication pathways remained functional during past storm damage, and which neighboring trees provided assistance during times of stress. This institutional memory allows oaks to make sophisticated decisions about resource allocation and partnerships development based on historical performance data. Oak behavior also reveals the network's capacity for long-term planning. These trees begin preparing for winter months before the first signs of autumn appear, gradually shifting their resource allocation to support fungal partners that will remain active during cold weather. They also engage in what can only be called investment strategies, channeling extra resources toward young trees that show promise for future network contributions, even when those investments provide no immediate benefit to the oak itself. The evergreen conifers exhibit behaviors that demonstrate their role as the network's essential infrastructure. Unlike deciduous trees that experience dramatic seasonal changes in activity, conifers maintain remarkably consistent behavioral patterns throughout the year. Their steady photosynthetic output provides a stable energy base that keeps the underground internet operational even during the coldest months. This consistency comes at a cost, as conifers must carefully balance their energy expenditure to avoid exhaustion during the long winter months when photosynthetic rates are reduced. Conifer behavior reveals sophisticated energy management strategies that would impress any efficiency expert. These trees can adjust their network contributions based on seasonal energy availability, reducing their support for energy-intensive network functions during winter while maintaining essential communication pathways. They also demonstrate remarkable resilience behaviors, automatically rerouting their fungal connections around damaged areas and quickly establishing backup communication channels when primary pathways are compromised. The fungal partners in this network exhibit behaviors that blur the line between individual organisms and network infrastructure. The mycorrhizal fungi operate according to behavioral principles that seem designed to optimize network performance rather than individual survival. These organisms constantly monitor the chemical signatures of their plant partners, adjusting their resource extraction and transport activities based on real-time assessments of tree health and nutritional needs. Fungal behavior reveals a form of active network management that rivals the most sophisticated artificial intelligence systems. When a fungal network detects that one of its tree partners is under attack by insects, it immediately begins increasing the production and transport of defensive compounds to that tree. Simultaneously, it sends chemical warning signals through the network to alert other trees in the area. This coordinated response requires the fungus to process multiple streams of chemical information and execute complex behavioral protocols in real time. The fungi also engage in what researchers call network optimization behaviors, continuously adjusting their hyphal networks to improve efficiency and redundancy. They can dissolve inefficient connections and grow new pathways that provide better resource transport or communication capabilities. This constant network remodeling allows the underground internet to adapt to changing conditions and maintain optimal performance even as trees grow, die, and are replaced over the decades. Perhaps most remarkably, some fungal species demonstrate behaviors that suggest they actively facilitate beneficial connections between trees. These network matchmaker fungi can detect chemical signatures that indicate compatibility between potential partners and will grow specialized connection pathways to introduce compatible trees to each other. This behavior goes far beyond simple resource transport, representing a form of network intelligence that actively works to improve system-wide connectivity and cooperation. The coordination between tree and fungal behaviors creates network-wide activity patterns that follow predictable daily and seasonal rhythms. Morning hours see peak resource production and distribution as trees channel their fresh photosynthetic output into the network. Midday periods focus on communication and coordination as chemical signals flow through the hyphal highways. Evening hours often feature resource consolidation and network maintenance as both trees and fungi prepare for the reduced activity of nighttime hours. These individual behaviors, when multiplied across thousands of trees and millions of fungal organisms, create a network that exhibits emergent properties far more sophisticated than the sum of its parts. The underground internet operates as a collective intelligence that can solve complex problems, adapt to changing conditions, and maintain itself across centuries of environmental change through the coordinated behaviors of its diverse participants. The first interactions between trees and fungi begin with a chemical conversation so subtle and sophisticated that it resembles a diplomatic negotiation between two intelligent civilizations. When a young tree seedling sends its tender roots exploring through the soil, it releases specific molecular signatures that announce its identity, nutritional needs, and potential offerings to the underground network. These chemical introductions travel through the soil like digital handshakes, carrying detailed information about the newcomer's species, health status, and genetic compatibility with potential fungal partners. The fungi respond to these molecular invitations with their own chemical credentials, each species broadcasting its unique capabilities and specializations. A fungal network specializing in phosphorus extraction sends signals rich with phosphorus indicating compounds, while fungi expert in water transport release moisture signaling molecules. This initial chemical dialogue establishes the foundation for partnerships that may last for decades, with both parties carefully evaluating each other's qualifications before committing to the energy investment required for network connection. The process of establishing a new network connection reveals the remarkable precision of fungal engineering. When a compatible match is detected, specialized fungal threads begin growing toward the tree roots, with the directed purpose of a construction crew following architectural blueprints. These hyphal threads navigate through the complex three-dimensional maze of soil particles, following chemical gradients with an accuracy that would challenge the most sophisticated GPS system. They can detect and respond to chemical signals from potential partners across distances that span several feet, demonstrating a form of molecular navigation that operates at scales far beyond human perception. The actual moment of connection between fungus and tree represents one of nature's most elegant engineering achievements. The fungal hyphae don't simply attach to the root surface, but instead engage in a complex interfacing process that creates a biological merger between two completely different organisms. Some fungi wrap their threads around root tips like living sheaths, creating external interfaces that maximize surface area for exchange. Others actually penetrate into root cells, forming internal networks that allow for even more intimate communication and resource sharing. Once established, these partnerships begin exhibiting interaction patterns that reveal the network's capacity for intelligent resource allocation. Trees experiencing abundant sunlight and rich soil conditions become net contributors to the network, channeling excess sugars and nutrients through their fungal partners to trees struggling in shadier or less fertile locations. This resource redistribution operates according to sophisticated algorithms that consider not just immediate need, but also the long-term health and potential contributions of recipient trees. The network's resource-sharing protocols demonstrate a form of biological economics that challenges traditional notions of competition in nature. A mature Douglas fir detecting drought stress in a neighboring maple will redirect water through the underground network, even though the two trees belong to different species and might normally be considered competitors for the same resources. This interspecies cooperation reveals interaction patterns based on mutual benefit rather than zero-sum competition, creating a forest economy where success is measured by network health rather than individual dominance. The communication aspects of these interactions operate with a sophistication that rivals human information networks. When a tree comes under attack by bark beetles, it releases specific alarm chemicals that are immediately detected by its fungal partners. These fungi then amplify and transmit the alarm signals through their hyphal networks, creating a cascade of chemical warnings that can reach trees hundreds of feet away within hours. The receiving trees respond by beginning production of defensive compounds, creating a forest-wide immune response triggered by a single tree's distress call. The network's information processing capabilities extend far beyond simple alarm systems. Trees and fungi engage in constant exchanges of environmental data, sharing information about soil conditions, water availability, nutrient concentrations, and seasonal changes. This ongoing data sharing allows the network to maintain a collective awareness of forest conditions that far exceeds what any individual organism could achieve alone. A tree experiencing the first signs of drought can access information from across the entire network to determine whether the dry conditions are localized or part of a broader pattern requiring coordinated response. The interaction patterns also reveal the network's capacity for learning and adaptation. Fungal partners that prove reliable during challenging conditions receive increased resource investments from their tree partners, while connections that fail to provide adequate support are gradually reduced or dissolved. This feedback system allows the network to optimize its connections over time, strengthening beneficial partnerships while eliminating unproductive relationships. The seasonal rhythms of forest life create predictable interaction patterns that demonstrate the network's temporal intelligence. As autumn approaches, deciduous trees begin systematically transferring their accumulated nutrients to their fungal partners for storage and redistribution. This process requires precise coordination between trees and fungi, as the timing of nutrient transfer must match the fungi's capacity for uptake and storage. The interaction becomes a carefully choreographed dance of chemical signals and resource flows that ensures maximum efficiency in the transition from active growing season to dormant winter period. Winter interactions reveal another layer of network sophistication as the partnership dynamics shift to accommodate the reduced activity levels of deciduous trees. Evergreen species increase their network contributions during this period, maintaining communication pathways and supporting fungal partners that will keep essential network functions operational. The fungi, in turn, adjust their resource allocation algorithms to account for the seasonal changes in energy availability, demonstrating a form of network load balancing that maintains system stability despite dramatic fluctuations in resource input. The interactions between different fungal species add another dimension of complexity to the network. Fungal that specialize in different types of resource extraction often share territories around the same tree roots, creating multi-species partnerships that provide comprehensive support for their plant partners. These fungal consortiums engage in their own forms of cooperation and resource sharing, creating sub-networks within the larger forest internet that optimize the delivery of specialized services to connected trees. The network's capacity for conflict resolution emerges when trees or fungi compete for the same resources. Rather than engaging in destructive competition, the network appears to have evolved mechanisms for negotiating resource allocation that minimize conflict while maximizing overall system efficiency. These negotiations are conducted entirely through chemical signaling, with participants exchanging molecular offers and counteroffers until mutually acceptable arrangements are reached. Perhaps most remarkably, the interaction patterns reveal the network's ability to facilitate new partnerships and expand its coverage into previously unconnected areas. Fungi actively recruit new tree partners by extending their networks into areas where young seedlings are establishing themselves. They provide initial support to help new trees connect to the network, even when those connections may not provide immediate benefits to the recruiting fungi. This altruistic behavior suggests that the network operates according to principles that prioritize long-term system growth and stability over short-term individual gains. These fundamental interaction patterns create the foundation for more complex network behaviors that emerge when thousands of individual partnerships combine to create system-wide intelligence and coordination capabilities that transform the forest from a collection of individual organisms into a unified, communicating ecosystem. The simple partnerships described in initial network connections evolve over decades into relationships of such complexity and interdependence that they fundamentally challenge our understanding of where one organism ends and another begins. These are not merely transactional exchanges between independent entities, but profound biological mergers that create hybrid organisms with capabilities far exceeding either partner alone. The underground internet succeeds precisely because it has transcended the limitations of individual identity, creating networks where the boundaries between self and other dissolve into something approaching a collective consciousness. The relationship between an ancient Douglas fir and its primary fungal partner represents one of nature's most sophisticated examples of interspecies cooperation. After 50 years of partnership, the fungal network has become so thoroughly integrated with the tree's root system that neither organism can survive without the other. The fungus has evolved specialized structures that interface directly with the tree's vascular system, creating biological unions where nutrients flow seamlessly between fungal and plant tissues.
The tree, in turn, has modified its root architecture to accommodate its fungal partners,
developing specialized cells that exist solely to support the partnership. This integration goes far beyond simple resource exchange. The fungal partner has become an extension of the tree's sensory system, dramatically expanding the tree's ability to perceive and respond to environmental conditions. Through its vast hyphal network, the fungus provides the tree with real-time information about soil conditions, weather patterns, and potential threats across an area spanning several acres. The tree processes this information through its own neural-like networks, making decisions that affect not just its own survival, but the welfare of its fungal partner and the entire network community. The dependency relationships within the network create a form of biological insurance system that protects against environmental catastrophes. When drought strikes a forest, trees with the most extensive fungal partnerships have access to water sources that can be hundreds of feet away from their own root systems. The fungi act as biological aqueducts, drawing moisture from deep groundwater sources, seasonal streams, and areas of higher soil moisture to support their plant partners. This water-sharing network can keep trees alive during droughts that would otherwise prove fatal, creating forest resilience that emerges from interdependence rather than individual toughness. The network's nutritional dependencies reveal equally sophisticated relationships. Different fungal species specialize in extracting specific nutrients from various soil components, creating a diversified supply chain that ensures trees have access to a complete nutritional profile, regardless of local soil deficiencies. Some fungi excel at breaking down organic matter to release nitrogen, while others specialize in dissolving mineral compounds to extract phosphorus or potassium. Trees that maintain partnerships with multiple fungal specialists gain access to a nutritional buffet that would be impossible for any individual root system to achieve alone. The protective relationships within the network demonstrate how interdependence creates collective security systems. When pathogenic fungi or harmful bacteria threaten the forest, the beneficial fungi respond with coordinated defense strategies that protect not just their immediate tree partners but the entire network community. Some fungal species produce powerful antibiotic compounds that create protective barriers around vulnerable trees, while others recruit beneficial microorganisms that outcompete harmful invaders. These defensive relationships create forest immunity that operates at the ecosystem level, protecting individual trees through network-wide resistance. The network's capacity for collective decision-making emerges from these complex interdependencies. When environmental stresses threaten the forest, the network engages in sophisticated resource allocation decisions that prioritize the survival of the most valuable community members. Mature trees, with the most extensive partnerships, receive priority support during crises, not because they are individually more important, but because their survival maintains the network infrastructure that supports dozens of other organisms, These decisions are made through chemical consensus processes that involve input from hundreds of fungal and plant partners across the affected area. The temporal dimensions of these relationships reveal how the network maintains continuity across centuries of environmental change.
The longest-lived partnerships between ancient trees and their fungal associates create living libraries that store information about past environmental conditions, successful survival strategies, and effective network configurations. When new challenges arise, the network can access this biological memory to identify proven responses and adapt successful strategies from previous eras. These ancient partnerships serve as the network's institutional memory, ensuring that hard-won evolutionary knowledge is preserved and transmitted to future generations. The network's reproductive strategies demonstrate how interdependence extends to the creation of new network participants. Mature trees don't simply release their seeds randomly into the environment, but instead coordinate their reproductive efforts with their fungal partners to ensure that offspring have the best possible chance of network integration. Fungi extend specialized hyphal networks to meet and support newly germinated seedlings, providing immediate access to network resources that dramatically improve survival rates. This coordinated reproduction creates forest regeneration patterns that maintain network continuity even as individual trees reach the end of their lifespans. The relationship dynamics also reveal the network's capacity for innovation and adaptation. When new environmental challenges arise, trees and fungi engage in experimental partnerships that test novel survival strategies. Some relationships involve fungi that have never before partnered with particular tree species, creating hybrid connections that explore new possibilities for resource sharing and environmental adaptation. These experimental partnerships allow the network to evolve new capabilities in response to changing conditions, ensuring that the forest internet remains relevant and effective even as the world around it transforms. The network's conflict resolution mechanisms demonstrate how interdependent relationships create stability even when individual interests might diverge. When resources become scarce, trees and fungi engage in sophisticated negotiation processes that balance individual needs against network welfare. These negotiations are conducted through chemical signaling systems that allow participants to communicate their needs, assess alternatives, and reach agreements that optimize overall network health. The dependency relationships ensure that no participant can pursue purely selfish strategies without damaging the partnerships they rely on for survival. Perhaps most remarkably, the network exhibits behaviors that suggest the emergence of collective consciousness from these interdependent relationships. During forest-wide crises, the network coordinates responses that require information processing and decision-making capabilities that far exceed what any individual organism possesses. The network can simultaneously monitor environmental conditions across vast areas, allocate resources according to complex priority systems, and implement coordinated response strategies that protect the entire forest community. These collective behaviors emerge from the interdependent relationships between thousands of organisms, creating a form of distributed intelligence that represents one of nature's most sophisticated information processing systems. The interdependencies within the underground internet create a forest ecosystem where individual survival depends entirely on network membership and active participation in collective welfare. Trees that attempt to operate independently quickly discover that their isolated efforts cannot match the capabilities available through network partnership. The most successful forest inhabitants are those that invest most heavily in their network relationships, contributing their unique capabilities to the collective while benefiting from the diverse strengths of their partners. These complex relationship dynamics transform the forest
from a collection of competing individuals into an integrated community where interdependence creates capabilities that emerge only through cooperation, demonstrating how evolution can favor collaboration over competition when the challenges of survival exceed what any individual organism can overcome alone. Beneath the visible interactions of trees and fungi lies a hidden world of molecular mechanisms so sophisticated they rival the most advanced human technologies. The underground internet operates through biochemical processes that function as living software, executing complex algorithms through chemical reactions that process information, make decisions and coordinate behaviors across the entire forest network. These molecular mechanisms represent millions of years of evolutionary programming, creating biological computers that operate according to principles far more elegant and efficient than anything human engineers have yet achieved. The foundation of the network's communication system rests on a vast lexicon of chemical signals that carry information with the precision of digital data packets. Each molecule serves as a biological bit of information, carrying specific meanings that can be decoded by receiving organisms. When a tree detects insect damage to its leaves, it produces a cocktail of volatile organic compounds that functions like a chemical telegram, encoding detailed information about the type of threat, its severity, and the specific defenses needed to counter it. These molecular messages travel through the air and through fungal networks, creating a multi-channel communication system that ensures critical information reaches its intended recipients through multiple pathways. The fungal networks process these chemical signals through molecular recognition systems that operate with the selectivity of sophisticated sensors. Specialized proteins embedded in fungal cell membranes act as biological receptors, each one designed to detect and respond to specific chemical signatures. When a distress signal from a tree binds to the appropriate receptor, it triggers a cascade of biochemical reactions that amplifies the signal and routes it through the hyphal network to other connected organisms. This molecular amplification system allows chemical signals that originate from a single tree to be detected by organisms across vast distances, creating forest-wide communication networks that operate through molecular relay systems. The resource transport mechanisms within the network demonstrate equally impressive molecular engineering. Fungi have evolved specialized molecular pumps that can actively transport nutrients against concentration gradients, moving resources from areas of abundance to regions of scarcity. These biological pumps operate through complex protein mechanisms that use energy to drive materials uphill, creating directed resource flows that defy the normal tendency of molecules to spread randomly through diffusion. The energy for these transport systems comes from the coordinated metabolic activities of both trees and fungi, creating biological supply chains powered by shared energy resources. The network's decision-making processes operate through molecular computing systems that process multiple streams of chemical information simultaneously. When a fungal network receives conflicting signals about resource allocation priorities, it integrates this information through biochemical pathways that function like biological logic circuits. Different chemical inputs interact through enzyme systems that perform logical operations, weighing various factors and producing chemical outputs that direct network behavior. These molecular decision-making systems can process complex, multivariable problems, optimizing resource allocation based on current conditions, historical data, and projected future needs. The timing mechanisms that coordinate network activities rely on molecular clocks that operate with remarkable precision. Trees and fungi maintain internal chemical oscillators that track daily and seasonal rhythms,
allowing them to coordinate their activities with the broader forest community. These biological timepieces operate through feedback loops, involving specific proteins that accumulate and degrade in regular cycles, creating cellular metronomes that keep network participants synchronized.
During critical periods like spring awakening or autumn nutrient withdrawal, these molecular clocks ensure that thousands of organisms coordinate their activities with split-second timing. The network's memory systems store information through molecular modifications that create chemical records of past experiences. Fungi can chemically tag their hyphal networks to encode information about successful partnerships, reliable resource sources, and effective response strategies. These molecular memories persist for years, allowing organisms to access accumulated wisdom from previous environmental challenges. Trees similarly encode memory in their cellular structures, using chemical modifications to their DNA and proteins to record information about past stresses, successful adaptations, and beneficial partnerships. The adaptive mechanisms within the network operate through molecular switches that can rapidly reconfigure biological processes in response to changing conditions. When environmental stresses are detected, specific chemical signals activate dormant genetic programs that alter cellular behavior, enzyme production, and resource allocation patterns. These molecular switches allow organisms to shift between different operational modes, transforming from growth-focused configurations during abundant periods to survival-oriented states during times of stress. The speed and precision of these molecular reconfiguration systems enable the network to respond to environmental changes faster than any mechanical system could achieve. The network's authentication mechanisms prevent infiltration by harmful organisms through molecular identification systems that operate like biological security protocols. Trees and beneficial fungi exchange specific chemical keys that verify their identities and establish trusted connections. These molecular handshakes involve complex sequences of chemical exchanges that are virtually impossible for pathogenic organisms to counterfeit. The authentication systems continuously monitor network connections, detecting and isolating any organisms that fail to provide proper chemical credentials. The quality control systems within the network maintain optimal performance through molecular monitoring mechanisms that continuously assess the health and efficiency of network connections. Fungi deploy specialized chemical sensors that monitor the flow rates, signal quality, and resource exchange ratios of their partnerships. When these molecular quality control systems detect declining performance in network connections, they trigger maintenance protocols that can repair damaged pathways, optimize resource flows, or dissolve inefficient partnerships. These ongoing quality assessments ensure that the network maintains peak performance even as individual components age or face environmental stresses. The network's error correction mechanisms operate through molecular redundancy systems that ensure reliable information transmission even when individual communication pathways are compromised. Critical chemical signals are transmitted through multiple hyphal pathways simultaneously, allowing the network to maintain communication even when some connections are damaged. The receiving organisms compare signals from different pathways and use molecular algorithms to identify and correct transmission errors, ensuring that important information reaches its destination with perfect fidelity. The encryption mechanisms that protect sensitive network communications involve molecular codes that scramble chemical information to prevent interception by competing organisms. Trees and their fungal partners share chemical encryption keys that allow them to encode and decode private communications about resource reserves, defensive strategies, and partnership negotiations. These molecular encryption systems ensure that sensitive network communications remain secure even in environments where potential competitors might attempt to eavesdrop on chemical signals. The network's upgrade mechanisms allow for continuous improvement of communication and resource-sharing protocols through molecular evolution systems that test and implement new chemical algorithms. When environmental pressures create demands for enhanced network capabilities, organisms experiment with new molecular mechanisms that might provide improved performance. Successful innovations are chemically encoded and shared through the network, allowing beneficial improvements to spread throughout the forest community. These molecular upgrade systems ensure that the underground internet continues to evolve and improve its capabilities over time. Perhaps most remarkably, the network exhibits molecular learning systems that allow it to improve its performance based on experience. Chemical feedback loops track the outcomes of different network decisions and adjust the molecular algorithms that guide future behaviors. When particular resource allocation strategies prove successful during environmental challenges, the chemical pathways that produce those strategies are strengthened and become more likely to be activated in similar future situations. This molecular learning creates a network that becomes increasingly sophisticated and effective over time, accumulating wisdom through chemical experience and encoding successful strategies in molecular memory systems that persist across generations. The molecular mechanisms revealed in the network's hidden operations combine to create survival techniques so advanced they represent evolutionary masterpieces of adaptation. These are not simple responses to environmental challenges, but sophisticated multi-generational strategies that demonstrate how the underground internet has transformed survival from an individual struggle into a collective art form. The network has evolved techniques that allow forests to survive catastrophes that would devastate any collection of individual organisms, creating resilience that emerges from the accumulated wisdom of millions of years of environmental challenges. The network's drought survival strategies reveal perhaps its most impressive adaptive achievements. When rainfall patterns shift and soil moisture levels begin to decline, the underground internet activates what can only be described as a biological water management system that rivals the most sophisticated urban infrastructure. The network begins by conducting a comprehensive assessment of water availability across the entire forest, using chemical sensors distributed through millions of fungal threads to create real-time maps of soil moisture conditions. This hydrological surveillance system can detect the early stages of drought weeks before individual trees would notice any stress. Once drought conditions are confirmed, the network implements a coordinated water conservation and redistribution protocol that transforms the forest into a single integrated organism focused on collective survival. Trees in areas with better water access automatically begin reducing their water consumption while increasing their contributions to the network's underground reservoir system. Fungi respond by growing specialized drought-resistant hyphal structures that can extract moisture from increasingly dry soils and transport it across vast distances to trees. In the most water-stressed locations, the network essentially creates biological pipelines that can move water hundreds of feet through underground channels, maintaining forest-wide hydration even when local conditions would normally prove fatal. The most remarkable aspect of the drought response involves the network's capacity for predictive adaptation. Using chemical information about atmospheric conditions, soil temperature patterns, and seasonal timing, the network can anticipate drought conditions before they fully develop. Trees begin modifying their physiology months in advance, reducing leaf surface area, deepening root systems,
and increasing their production of drought-resistant compounds. The fungi simultaneously strengthen their hyphal networks and increase their water storage capabilities, creating biological reservoirs that can sustain the forest through extended dry periods. The network's fire survival adaptations demonstrate equally sophisticated evolutionary engineering. Rather than simply enduring wildfires, the underground internet has evolved to use fire as a tool for forest renewal and strengthening. When fire sweeps through a forest, the network's underground infrastructure remains largely intact, protected by the insulating properties of soil and the fire-resistant structures that fungi have evolved specifically for post-fire recovery. Immediately after a fire, the surviving network springs into action with a coordinated regeneration protocol that transforms destruction into opportunity. The post-fire recovery process reveals the network's capacity for rapid ecosystem rebuilding that exceeds anything possible through individual tree efforts. The surviving fungal networks immediately begin extending into burned areas, creating infrastructure for new growth before the first seeds have even germinated. These pioneer fungi establish resource distribution networks that will support incoming seedlings, creating biological nurseries that dramatically improve survival rates for new growth. The network can distinguish between different types of seeds and direct appropriate resources to support the specific needs of each species, creating diverse forest regeneration that optimizes ecological resilience. The network's pathogen resistance strategies demonstrate how collective immunity can provide protection that no individual organism could achieve alone. When disease-causing fungi or bacteria threaten the forest, the underground internet responds with coordinated defense systems that operate at multiple scales simultaneously. Individual trees increase their production of antimicrobial compounds, while their fungal partners recruit beneficial microorganisms that can outcompete harmful invaders. The network creates biological quarantine zones around infected areas, concentrating defensive resources to prevent disease spread while simultaneously developing and testing new resistance strategies. Perhaps most impressively, the network exhibits adaptive immunity that allows it to develop enhanced resistance to pathogens through exposure and learning. When a new disease enters the forest, the network initially responds with general defense mechanisms while gathering chemical information about the invader's characteristics and vulnerabilities. Over time, the network develops increasingly specific and effective responses, eventually creating targeted biological weapons that can eliminate the pathogen with surgical precision. This adaptive immunity is encoded in the network's molecular memory systems and can be rapidly activated if the same pathogen returns in future years. The network's climate adaptation strategies reveal how the underground internet prepares for and responds to long-term environmental changes that span decades or centuries. As climate patterns shift, the network begins gradually modifying the forest composition by selectively supporting tree species that are better adapted to projected future conditions. This climate adaptation occurs through subtle changes in resource allocation that favor heat-tolerant or drought-resistant species, while gradually reducing support for species that may struggle under future climate scenarios. The network's migration facilitation systems enable forests to essentially move across landscapes in response to changing climate conditions. When environmental conditions begin favoring different locations, the network coordinates seed dispersal and establishment activities that create new forest patches in more favorable areas. The fungi extend their networks to connect these new forest patches with established communities, creating biological corridors that allow for genetic exchange and resource sharing across vast distances. Over centuries,
This migration facilitation allows entire forest ecosystems to relocate in response to climate changes while maintaining their network integrity. The network stress hardening techniques prepare forest communities for increasing environmental uncertainty by deliberately exposing trees to controlled stresses that build resilience. During periods of abundance, the network occasionally restricts resources to certain trees, creating artificial stress conditions that trigger adaptive responses and strengthen cellular defenses. These controlled stress exposures function like biological vaccinations, preparing trees to better survive genuine environmental challenges when they occur. The network's genetic optimization strategies demonstrate how the underground internet actively influences forest evolution to enhance collective survival capabilities. The network can selectively support trees with favorable genetic traits by providing them with enhanced resources and better partnership opportunities. Over generations, this selective support gradually increases the frequency of beneficial genes within the forest population, creating directed evolution that optimizes forest characteristics for network compatibility and collective resilience. The network's energy efficiency innovations reveal how the underground internet continuously develops new techniques for optimizing resource utilization. Fungi evolve increasingly efficient transport mechanisms that can move resources with minimal energy expenditure, while trees develop metabolic optimizations that maximize their contributions to network energy pools. These efficiency improvements compound over time, creating forests that can maintain higher levels of biological activity with lower resource inputs. The network's redundancy systems ensure survival even when major components are lost to catastrophic events. Critical network functions are distributed across multiple organisms and pathways so that the loss of any individual tree or fungal partner cannot compromise essential network operations. The network maintains backup systems for communication, resource storage, and coordination functions, creating biological redundancy that provides unprecedented resilience against environmental disasters. These sophisticated adaptation and survival techniques transform forests from vulnerable collections of individual organisms into resilient ecosystems capable of surviving and thriving through environmental challenges that would overwhelm any single species, demonstrating how evolution can create collective intelligence and adaptive capabilities that emerge only through the coordinated efforts of diverse biological communities, working together through underground networks of mutual support and shared wisdom. When viewed from above, a forest appears as a collection of individual trees scattered across the landscape. But beneath the surface lies an interconnection architecture so intricate and purposeful that it transforms our understanding of what constitutes a single organism. The underground internet operates as a vast neural network where every tree serves as a processing node, and every fungal connection functions as a biological synapse, creating forest-wide intelligence that emerges from the coordinated activities of millions of individual components working in perfect synchronization. The network topology of a mature forest reveals organizational principles that mirror the most sophisticated human communication systems, yet exceed them in complexity and adaptability. Hub trees, typically the oldest and largest specimens, serve as major network routers with hundreds of direct connections radiating outward through the forest. These biological internet service providers maintain the backbone infrastructure that enables communication between distant forest regions, processing and routing chemical information with the efficiency of advanced computer networks. Around each hub tree, smaller trees form interconnected clusters that function like local area networks, sharing resources and information within their immediate neighborhoods. while maintaining connections to the broader forest-wide web. The redundancy built into the network's interconnection patterns ensures that no single point of failure can compromise forest-wide communication. Multiple pathways connect every tree to the network through diverse routes that automatically reroute around damaged connections.
When storms topple major hub trees or disease eliminates key network nodes, the surviving connections rapidly strengthen and new pathways develop to maintain network integrity. This biological fault tolerance creates forest communication systems that remain operational even after catastrophic disruptions that would cripple human-engineered networks. The network's data flow patterns reveal sophisticated traffic management protocols that optimize information transmission across the forest. High-priority signals like pathogen warnings receive priority routing through the fastest hyphal pathways, while routine resource allocation data travels through standard channels that conserve network capacity for emergency communications.
During peak activity periods, the network automatically load balances its traffic, distributing communication flows across multiple pathways to prevent bottlenecks and ensure that critical information reaches its destinations without delay. The forest's resource distribution networks operate according to economic principles that create stable, efficient markets for biological goods and services. Trees contribute their photosynthetic products to network-wide resource pools, while fungi provide extraction and transport services that make soil nutrients accessible to the entire community.
The network maintains dynamic pricing mechanisms where resources become more valuable during scarcity and less costly during abundance, creating market forces that automatically optimize resource allocation without requiring central planning or control. The interconnection patterns also reveal the network's capacity for collective decision-making that transcends individual intelligence. When environmental challenges require coordinated responses, the network processes information from thousands of individual sensors to create comprehensive situational assessments that inform forest-wide strategy decisions.
These collective intelligence processes operate through distributed consensus mechanisms where individual trees and fungi contribute their local knowledge to network-wide decision-making algorithms that produce responses more sophisticated than any individual organism could generate alone. The network's learning systems demonstrate how interconnected biological communities can accumulate and share knowledge across vast scales of space and time. Individual experiences with environmental challenges, successful adaptation strategies, and effective partnerships are encoded in chemical memory systems that become accessible to the entire network.
New trees connecting to established networks immediately gain access to centuries of accumulated wisdom, learning from the experiences of thousands of previous forest inhabitants without having to repeat dangerous trial-and-error experiments. The seasonal coordination patterns within the network reveal how interconnected systems can synchronize complex behaviors across enormous biological communities. As environmental conditions change throughout the year, the network coordinates the activities of thousands of organisms to optimize collective performance. Spring awakening involves precisely timed sequences where different species activate their growth and reproductive systems in coordinated waves that maximize resource utilization and minimize competition. Autumn preparation similarly requires synchronized resource withdrawal and storage activities that ensure network stability through winter dormancy periods. The network's response to external threats demonstrates how interconnected systems can mount coordinated defenses that provide protection beyond what individual organisms could achieve.
When invasive species enter the forest, the network rapidly mobilizes collective resistance that includes chemical warfare, resource restriction, and coordinated competitive responses designed to overwhelm and exclude the invaders. These biological immune responses operate through network-wide communication systems that can organize defensive actions across vast areas within hours of threat detection. The interconnection patterns also enable the network to engage in long-term ecosystem engineering that shapes environmental conditions to favor network expansion and optimization. Forests actively modify their local climate by coordinating transpiration patterns that increase humidity and moderate temperature extremes. The network influences soil chemistry by coordinating the types and quantities of chemical compounds released by tree roots and fungal partners, gradually creating soil conditions that optimize network performance. Over decades, these ecosystem engineering activities transform landscapes to better support the underground internet infrastructure. The network's growth patterns reveal how interconnected biological systems can coordinate expansion into new territories while maintaining connection to established communities. Pioneer trees and fungi work together to establish network beachheads in unforested areas, creating initial infrastructure that can support subsequent waves of forest expansion. These biological colonization efforts involve sophisticated coordination between established forest networks and pioneer organisms, ensuring that new forest patches develop with optimal network connectivity from their earliest stages. The network exhibits scale-free connectivity patterns where a few highly connected hub nodes maintain the majority of network connections while most nodes have relatively few direct links. This architecture provides optimal efficiency for information transmission and resource distribution while maintaining remarkable resilience against random failures. The hub trees that serve as major network nodes typically develop enhanced networking capabilities that allow them to manage hundreds of simultaneous connections without compromising their individual health or performance. The network's modularity enables different forest regions to specialize in particular functions while maintaining overall system integration. Some areas develop into resource production centers that generate surplus energy and materials for distribution throughout the network. Other regions become specialized processing centers that concentrate on particular biological functions like pathogen resistance, genetic diversity maintenance, or environmental monitoring. These functional specializations increase overall network efficiency while creating interdependencies that strengthen forest-wide cooperation and coordination. The dynamic reconfiguration capabilities of the network allow it to rapidly restructure its connections in response to changing conditions or new opportunities. When environmental conditions shift or new resources become available, the network can quickly grow new connections and dissolve inefficient pathways to optimize its configuration for current circumstances. This biological adaptability enables forests to maintain optimal performance even as their internal and external environments undergo constant change. The network's emergence patterns demonstrate how simple local interactions between neighboring organisms can generate complex system-wide behaviors that transcend the capabilities of individual components. The sophisticated forest-level intelligence, coordinated ecosystem responses, and long-term strategic planning capabilities emerge spontaneously from the interconnected activities of trees and fungi, following relatively simple local rules for cooperation, resource sharing, and information exchange. These interconnection patterns create forest ecosystems that function as integrated superorganisms with collective intelligence, distributed memory, coordinated behavior, and adaptive capabilities that represent some of the most sophisticated biological systems on Earth, demonstrating how evolution can create network-based life forms that achieve capabilities impossible for individual organisms through the power of coordinated biological cooperation, operating at unprecedented scales of complexity and integration. From the vast network of interconnected relationships emerges something unprecedented in the natural world, a forest-level consciousness that exhibits behaviors, decision-making capabilities, and adaptive intelligence that transcend anything possible at the scale of individual organisms. This emergent forest mind operates through the collective processing power of millions of biological components working in coordination, creating a form of distributed intelligence that can solve complex problems, anticipate future challenges, and implement sophisticated strategies that span decades or centuries. The underground internet has evolved beyond a mere communication network into something approaching a biological brain that thinks in geological time and coordinates responses across entire ecosystems. The forest's weather prediction capabilities demonstrate this emergent intelligence in ways that challenge our understanding of biological cognition. Through its vast sensor network of fungal threads and root systems, the forest continuously monitors atmospheric pressure, humidity gradients, temperature fluctuations, and subtle chemical changes that precede weather pattern shifts. This biological meteorological system can detect the early stages of drought, storm systems, or seasonal changes days or weeks before they become apparent to human observers. The forest responds to these predictions by preemptively adjusting its resource allocation, strengthening vulnerable trees, and preparing defensive strategies that minimize damage from anticipated weather events. The forest's capacity for strategic resource management reveals decision-making processes that operate like a sophisticated economic planning system. During years of abundant rainfall and optimal growing conditions, the forest network makes coordinated investments in long-term infrastructure development, growing additional fungal networks, deepening root systems, and establishing new partnerships that will provide resilience during future challenging periods. Conversely, when environmental conditions suggest upcoming scarcity, the forest implements coordinated conservation measures that reduce resource consumption while building strategic reserves that can sustain the community through difficult times. Perhaps most remarkably, the forest exhibits what can only be described as maternal behavior toward its younger members, demonstrating emergent caring intelligence that transcends simple resource allocation. Mature forest networks actively nurture seedlings and young trees through sophisticated support systems that provide not just nutrients and water, but also information and protection. The forest can identify promising young trees and channel additional resources toward their development, while simultaneously recognizing struggling individuals and providing intensive care that dramatically improves their survival prospects. This nurturing behavior suggests a form of collective wisdom that recognizes the long-term value of investing in future network participants. The forest's conflict resolution capabilities reveal emergent diplomatic intelligence that maintains community stability even when individual interests might conflict. When different trees or fungal networks compete for the same resources, the forest deploys sophisticated mediation mechanisms that negotiate mutually acceptable solutions. These biological diplomatic processes involve complex exchanges of chemical signals that communicate needs, assess alternatives, and reach agreements that optimize overall network welfare while respecting individual requirements. The forest essentially functions as its own international relations system, maintaining peace and cooperation across diverse biological communities. The forest's innovation and experimentation behaviors demonstrate emergent creative intelligence that continuously develops new solutions to environmental challenges. When faced with novel threats or opportunities, the forest network engages in coordinated experimental programs that test different response strategies simultaneously across multiple locations. These biological research and development initiatives allow the forest to rapidly evaluate new approaches and implement successful innovations throughout the entire network. The forest learns from both successful and failed experiments, continuously improving its problem-solving capabilities through adaptive trial and error processes. The forest's memory consolidation systems reveal emergent archival intelligence that preserves and organizes accumulated knowledge for future reference. The network continuously processes experiences from across the forest, identifying successful strategies, recording environmental patterns, and encoding important information in molecular memory systems that persist across generations. This biological library system allows forests to access relevant knowledge from decades or centuries of previous experience, applying historical wisdom to contemporary challenges and avoiding the repetition of past mistakes. The forest's predictive modeling capabilities demonstrate emergent analytical intelligence that can anticipate future conditions and prepare appropriate responses. By analyzing patterns in environmental data, resource availability, and community health metrics, the forest network generates biological forecasts that guide long-term planning decisions. These predictive models influence everything from reproductive timing and partnership formation to resource allocation and infrastructure development, allowing forests to position themselves advantageously for projected future conditions. The forest quality control systems exhibit emergent management intelligence that maintains optimal network performance through continuous monitoring and optimization. The network continuously assesses the efficiency of its partnerships, the reliability of its communication pathways, and the effectiveness of its resource distribution systems. When performance metrics indicate declining efficiency, the forest implements corrective measures that can include partnership restructuring, pathway optimization, or component replacement, ensuring that network performance continues to improve over time. The forest's emergency response capabilities reveal emergent crisis management intelligence that can coordinate complex disaster responses across vast areas. When catastrophic events like fires, storms, or disease outbreaks threaten forest communities, the network rapidly mobilizes coordinated response systems that include resource redistribution, communication prioritization, damage containment, and recovery planning. These emergency responses operate with the efficiency and coordination of professional disaster management organizations, demonstrating the forest's capacity for sophisticated crisis leadership. The forest's cultural transmission systems demonstrate emergent educational intelligence that passes knowledge and successful strategies from experienced network participants to newcomers. Young trees connecting to established networks receive not just resources but also information about local conditions, successful survival strategies, beneficial partnerships, and potential threats. This biological education system ensures that accumulated forest wisdom is preserved and transmitted across generations, creating continuity of knowledge that spans centuries of environmental change. The forest's adaptive evolution capabilities reveal emergent design intelligence that can modify its own structure and capabilities in response to changing requirements. The network can selectively encourage the development of new traits, partnerships, and capabilities that enhance its overall performance, essentially engaging in directed evolution that optimizes forest characteristics for current and projected future conditions. This biological self-improvement system allows forests to continuously enhance their capabilities without waiting for random evolutionary changes. The forest's ecosystem engineering behaviors demonstrate emergent environmental intelligence that actively modifies surrounding conditions to optimize network performance. Forests coordinate their activities to influence local climate patterns, soil chemistry, water cycles, and atmospheric composition, creating environmental conditions that enhance their own survival and growth prospects. These ecosystem modifications represent large-scale environmental management projects that transform entire landscapes to better support forest network operations. The forest communication with other ecosystems reveals emergent diplomatic intelligence that enables coordination between different biological communities. Forest networks can exchange information and resources with adjacent grasslands, wetlands, or other forest systems, creating larger biological alliances that provide mutual support and shared defense against environmental challenges. These inter-ecosystem relationships demonstrate the forest's capacity for building strategic partnerships that extend far beyond its immediate boundaries. The forest's legacy planning systems exhibit emergent generational intelligence that makes decisions based on their long-term impact on future forest communities. The network invests in infrastructure development, genetic diversity maintenance, and knowledge preservation activities that may not provide immediate benefits, but will enhance the capabilities and resilience of future generations. This biological stewardship demonstrates the forest's capacity for long-term thinking that prioritizes sustainable development over short-term gains. These emergent properties transform forests from collections of individual organisms into unified biological civilizations with collective intelligence, shared memory, coordinated behavior, and adaptive capabilities that represent some of the most sophisticated forms of life on Earth, demonstrating how evolution can create network-based consciousness that achieves capabilities impossible for individual organisms through the power of coordinated biological cooperation and collective intelligence, operating across unprecedented scales of complexity, integration, and temporal continuity. The forest's emergent intelligence operates across temporal scales that dwarf human comprehension, weaving together daily rhythms, seasonal cycles, decadal patterns, and evolutionary processes into a unified biological symphony that has been playing for hundreds of millions of years. This temporal consciousness allows forests to simultaneously respond to immediate challenges while implementing strategies that unfold across centuries, creating a form of biological wisdom that emerges from the integration of multiple time streams into coherent long-term intelligence. The underground internet functions as both a real-time communication network and a temporal bridge that connects the forest's ancient past with its projected future. The daily cycles of forest activity reveal the network's capacity for precise temporal coordination across millions of individual organisms. Each dawn triggers a synchronized awakening that begins with the deepest fungal networks and ripples upward through root systems to eventually reach the forest canopy in perfectly coordinated waves. This biological sunrise involves the activation of countless molecular clocks that have been synchronized through chemical signaling, creating forest-wide circadian rhythms that optimize photosynthetic efficiency and resource distribution throughout each 24-hour period. The network can adjust these daily rhythms in response to seasonal changes, weather patterns, and environmental stresses, demonstrating temporal flexibility that maintains optimal performance under varying conditions. The forest's seasonal transitions reveal even more sophisticated temporal intelligence that anticipates and prepares for cyclical environmental changes months in advance. As summer progresses toward autumn, The network begins implementing coordinated preparation protocols that involve gradual resource withdrawal, partnership restructuring, and metabolic adjustments that optimize forest survival through winter dormancy periods. These seasonal transitions require precise timing that coordinates the activities of species with different biological rhythms, creating forest-wide synchronization that maximizes efficiency while minimizing waste during critical transition periods. The network's decadal patterns demonstrate how forest intelligence operates across timescales that span multiple human generations. Forest networks maintain long-term strategies for resource management, partnership development, and infrastructure growth that unfold over periods measured in decades. These extended planning horizons allow forests to invest in slow-developing capabilities that provide long-term competitive advantages, such as deep soil network development, genetic diversity optimization, and resistance building against environmental challenges that occur on irregular 10 to 20-year cycles. The forest's response to century-scale climate patterns reveals temporal intelligence that can detect and adapt to environmental changes that unfold across multiple tree lifespans. The network maintains biological memory systems that encode information about past climate variations, allowing it to recognize emerging patterns and implement appropriate adaptive responses. When gradual climate shifts begin altering temperature patterns, precipitation cycles, or seasonal timing, the forest responds with coordinated adaptations that may take decades to fully implement but position the ecosystem advantageously for projected future conditions. The evolutionary context of the underground internet reveals how forest intelligence has developed through millions of years of gradual refinement and adaptation. The partnership between trees and fungi that forms the foundation of forest networks represents one of evolution's most successful experiments in cooperative intelligence, having survived multiple mass extinction events and adapted to dramatic environmental changes throughout Earth's history. This evolutionary perspective demonstrates how the network's current capabilities emerged from countless generations of environmental challenges that gradually selected for increasingly sophisticated coordination and communication abilities. The forest's genetic memory systems preserve evolutionary wisdom that spans millions of years, encoding successful survival strategies, effective partnership configurations, and adaptive responses to environmental challenges in molecular archives that persist across countless generations. These genetic libraries allow forests to access solutions to environmental problems that may have last occurred thousands or millions of years ago, providing biological precedents for responding to rare but potentially catastrophic challenges. The network can activate dormant genetic programs that encode responses to environmental conditions that current forest inhabitants have never experienced, demonstrating how evolutionary memory enables rapid adaptation to unprecedented challenges. The network's evolutionary experimentation capabilities reveal how forests actively participate in their own evolutionary development through coordinated biological research programs. Rather than waiting for random genetic mutations to provide adaptive advantages, forest networks engage in systematic experimentation with new partnership configurations, communication protocols, and resource management strategies. These biological innovation programs accelerate evolutionary adaptation by testing multiple approaches simultaneously and rapidly implementing successful innovations throughout the network, effectively speeding up evolutionary processes through coordinated intelligence. The forest's co-evolutionary relationships demonstrate how network intelligence has shaped the evolution of countless other species that depend on forest ecosystems. The underground internet has influenced the evolutionary development of insects, birds, mammals, and countless other organisms by creating environmental conditions that favor particular traits and behaviors. This co-evolutionary influence extends the forest's temporal intelligence beyond its own biological boundaries, shaping the evolutionary trajectories of entire biological communities across geological timescales. The network's climate regulation capabilities reveal how forest intelligence operates as a planetary-scale temporal system that influences global environmental conditions across millennial timescales. Forests actively participate in regulating Earth's carbon cycle, water cycle, and atmospheric composition through coordinated activities that span continents and persist across multiple human civilizations. These planetary-scale effects demonstrate how local forest intelligence connects to global environmental systems, creating temporal feedback loops that influence planetary conditions across geological time periods. The forest's extinction recovery capabilities demonstrate temporal resilience that enables network intelligence to survive and recover from catastrophic environmental disruptions. The underground internet has evolved mechanisms that can preserve essential network functions through mass extinction events, allowing forest intelligence to rapidly re-establish itself once environmental conditions improve. These survival capabilities include dormancy systems that can maintain network infrastructure through extended adverse periods, as well as rapid recolonization protocols that can quickly restore forest connectivity across devastated landscapes. The network's future planning capabilities reveal how forest intelligence makes decisions based on projected environmental conditions that may not materialize for centuries. The forest invests in long-term adaptive strategies that prepare for climate scenarios, evolutionary pressures, and environmental challenges that extend far beyond the lifespans of current network participants. This future-oriented thinking demonstrates temporal intelligence that prioritizes long-term ecosystem sustainability over short-term optimization, creating forest strategies that remain effective across multiple environmental transitions. The forest's temporal integration systems unify information and decision-making across all these time scales, creating coherent intelligence that can simultaneously optimize daily resource allocation, coordinate seasonal transitions, implement decadal strategies, adapt to century-scale climate changes, and preserve evolutionary wisdom across millions of years. This temporal integration represents one of biology's most sophisticated achievements, creating network consciousness that transcends the temporal limitations of individual organisms through collective intelligence that operates across geological timescales. The underground internet demonstrates how evolution can create biological systems that think in deep time, making decisions that optimize outcomes across temporal scales that span from microseconds to millions of years. This temporal continuousness allows forests to function as living bridges between Earth's ancient past and its projected future, preserving evolutionary wisdom while continuously adapting to changing conditions through network intelligence that operates as both historical archive and future planning system. The forest's role as a temporal guardian reveals how network intelligence serves as a biological repository for Earth's environmental history and a planning system for planetary future sustainability. Through deep temporal consciousness and evolutionary continuity, forest networks preserve essential information about Earth's environmental systems while actively working to maintain planetary conditions that can support complex life
across future geological periods, demonstrating how local biological intelligence can scale up to become a planetary survival system operating across the deepest scales of evolutionary time.
The underground internet of the forest reveals universal principles that extend far beyond the boundaries of any single ecosystem, offering profound insights into the fundamental nature of intelligence, cooperation, and life itself. What we have discovered beneath our feet represents more than a fascinating biological phenomenon. It provides a blueprint for understanding how complex systems can emerge from simple cooperative relationships, how intelligence can arise from collective rather than individual consciousness, and how survival can be optimized through mutual aid rather than competitive struggle. The lessons learned from the forest's underground networks challenge our most basic assumptions about how life organizes itself and suggest revolutionary approaches to solving humanity's greatest challenges. The principle of distributed intelligence that governs forest networks offers transformative insights for human society and technology. Rather than centralizing decision-making in hierarchical structures, the forest demonstrates how sophisticated problem-solving can emerge from the coordinated activities of countless individual participants, each contributing their unique capabilities to collective intelligence that transcends any individual capacity. This biological model suggests possibilities for human organizations, technological systems, and social structures that could achieve unprecedented levels of adaptability, resilience, and innovation through distributed cooperation rather than centralized control. The forest's resource-sharing economy reveals economic principles that challenge fundamental assumptions about scarcity, competition, and wealth distribution. The underground internet operates according to abundance thinking, where resources flow automatically to where they are most needed regardless of the recipient's ability to pay or compete. This biological economy demonstrates how systems can thrive when success is measured by collective welfare rather than individual accumulation, suggesting economic models that could address inequality, resource depletion, and environmental degradation through cooperative abundance rather than competitive scarcity. The communication protocols of the underground internet offer revolutionary insights for human information systems and social networks. The forest's chemical communication operates with remarkable efficiency, transmitting only essential information while avoiding the noise and misinformation that plague human communication networks. The biological principles of signal authentication, priority routing, and network redundancy could inspire communication technologies that enhance understanding while reducing manipulation, creating information ecosystems that serve collective wisdom rather than individual power. The forest's approach to conflict resolution provides models for human diplomacy and social harmony that transcend traditional win-lose thinking. The underground network demonstrates how competing interests can be resolved through patient negotiation processes that seek mutually beneficial solutions rather than dominance by the strongest party. These biological mediation systems suggest approaches to international relations, community disputes, and personal conflicts that could achieve sustainable peace through cooperative problem-solving rather than adversarial competition. The temporal intelligence of forest networks offers profound insights for human planning and decision-making across multiple timescales. The forest's ability to simultaneously optimize short-term performance while implementing long-term strategies that span centuries provides a model for addressing challenges like climate change, resource management, and technological development that require coordination across multiple human generations. The biological principles of deep time thinking could inspire political and economic systems that prioritize long-term sustainability over short-term gains. The adaptive resilience demonstrated by forest networks reveals strategies for building human systems that can survive and thrive through uncertain and rapidly changing conditions. The underground Internet's ability to rapidly reconfigure itself in response to disruptions while maintaining essential functions offers blueprints for infrastructure, organizations, and communities that could maintain stability and effectiveness despite unexpected challenges. These biological resilience principles could inform approaches to everything from urban planning and supply chain management to education and healthcare systems. The forest's nurturing approach to young and struggling members provides models for human social systems that could optimize collective potential through mutual care and support. The underground network's investment in seedlings and vulnerable trees demonstrates how communities can thrive by ensuring that all members have access to the resources and opportunities they need to contribute their unique capabilities. These biological principles suggest educational, economic, and social policies that could unlock human potential through inclusive support rather than selective competition. The innovation and experimentation capabilities of forest networks offer insights for human creativity and technological development that could accelerate beneficial change while minimizing harmful consequences. The forest's approach to testing new strategies through distributed experimentation while maintaining system stability provides models for technological innovation, social change, and organizational development that could achieve rapid beneficial adaptation without catastrophic risk-taking. These biological innovation principles could inspire research and development approaches that optimize learning while minimizing negative side effects. The forest's ecosystem engineering capabilities reveal how conscious beings can actively improve their environments through coordinated action rather than exploitative extraction. The underground network's ability to modify soil chemistry, climate patterns, and environmental conditions to benefit all network participants demonstrates how intelligent systems can enhance their surroundings through cooperative construction rather than competitive consumption. These biological principles could inspire human approaches to environmental management, urban development, and planetary stewardship that create abundance through regenerative collaboration. The forest's integration of diversity as a source of strength rather than a challenge to overcome offers profound insights for human communities struggling with differences in culture, perspective, and capability. The underground network succeeds precisely because it brings together organisms with different specializations, creating collective capabilities that emerge from diversity rather than uniformity. These biological principles suggest approaches to human community building, organizational management, and international cooperation that could transform differences from sources of conflict into foundations for collective strength. The forest's demonstration that intelligence can emerge from cooperation rather than competition challenges fundamental assumptions about consciousness, cognition, and the nature of mind itself. The underground Internet reveals how sophisticated thinking, memory, and decision-making can arise from the coordinated activities of countless individual participants, suggesting that consciousness may be a collective property rather than an individual attribute. This biological perspective on intelligence could revolutionize approaches to artificial intelligence, education, and human cognitive development. The universal principles revealed by the forest's underground Internet suggest that cooperation, rather than competition, may be the fundamental organizing principle of complex systems throughout the universe. From the cellular cooperation that creates multicellular organisms to the planetary cooperation that maintains global environmental stability, the patterns observed in forest networks may represent universal laws of how complex systems emerge, survive, and thrive across all scales of existence. The forest teaches us that intelligence, consciousness, and wisdom may be emergent properties that arise naturally when diverse entities cooperate in networks of mutual support and shared benefit. This revelation transforms our understanding of what it means to be intelligent, suggesting that the highest forms of consciousness may emerge not from individual brilliance, but from our capacity to connect, communicate, and collaborate in networks that transcend the limitations of any single mind or species. The underground internet of the forest ultimately reveals that we live in a world where cooperation creates abundance, diversity generates strength, and collective intelligence emerges from networks of mutual care and shared wisdom. These universal principles offer hope that humanity can learn to organize itself according to the same collaborative principles that have enabled forests to thrive for hundreds of millions of years, creating human civilizations that flourish through cooperation rather than competition, abundance rather than scarcity, and collective wisdom rather than individual dominance. In recognizing the profound intelligence that exists beneath our feet, we discover not just the hidden workings of forest ecosystems, but universal principles that could guide humanity toward a future of unprecedented cooperation, sustainability, and collective flourishing that emerges from our capacity to learn from the ancient wisdom of the underground internet that has been operating beneath our feet throughout our entire evolutionary history.